That's why.
Yeah, the photocopier is Satan. Is this really the first thing I'm saying on my first recorded lesson? Well, here we are. Anyway, the photocopier is Satan, and it doesn't like to staple things or hole punch them correctly. Oh, yeah. Oh, I stole it real good. Real good. Also, I'm trying a new font combination this year, and I want you to let me know what you think. I'm not sold on it completely yet. It's a little plain for me, but yeah, a new font combo for 2019. Okay, we're gonna get going in chemistry. Chemistry is. Thank you so much. Chemistry is the study of the universe itself. If you're of a religious disposition, then chemistry is sort of the study of God's handwriting. And if you're not, then that will sound flowery and silly. But really and truly, chemistry is the study of how every single thing you've ever seen or felt or loved or hated or interact with works. How all of it works, what all of it is made of. And it's a pretty cool thing that life on Earth has been around for a few billion years at this point, and it's really only for about the last couple of hundred years that we've known anything about this. It's kind of interesting. You live in a unique time in the history of the universe where, to the best of our knowledge, very few living things as a percentage of what's been around have ever had the chance to know about this stuff. It's pretty cool. Hopefully, one day we'll discover that there's lots of other species out there that are also sitting in a chemistry class right now, enjoying themselves immensely. But in the meantime, I want to remember from grade 9, what do we remember? What is matter? What is the stuff that the universe is made out of? Very good. So matter is anything that has mass, and we usually put a second half to that. We say it has mass and that it, that's the same thing, though that's true. Not only does it weigh something, but it also it exists, absolutely. It occupies space, very good. All right, so matter is something that has mass and occupies space. If you found that you went a little too side, just like highlight and slide it over, just like that. It'll really help. So it has mass, it occupies space. What else can we say about it? Oh, how quickly we forget grade 9 science. I want you to know that I'm judging whoever taught you. That guy sucks. Yeah. Ooh. Oh, see, this is good. Yeah. It's made up of particles, and we'll get to what those are. And if you remember, we talked about the particle theory of matter, and it said, what about those particles? You're made of a bunch of individual little pieces, and those particles are what? What can you tell me about them? Yeah, definitely. Atoms. What else about them? You are made of particles, and the particles in you right now are doing what? Yeah, those atoms can come together to make molecules, definitely. I'm not going to write it because we're going to talk later, but that's true for sure. Remember particle theory of matter? We said these things are always, yeah, they're always moving. In fact, that motion can tell you something. If a piece of matter has particles that are moving really, really fast, what would be true about that matter the way we would experience it? Yeah, it'd be really hot, right? If the particles are really bouncing around, we experience that as high heat. If it has particles that are moving really slowly, we would experience that matter how? Yeah, it'd be real cold. So those particles are always in motion. The other thing is they're very small, which means matter is mostly what? If you zoomed in on you, you would discover that you, solid though you may appear, are in fact mostly made up of not even air. You're mostly empty space, actually. In fact, you are like 99.9999999% empty space. The particles that make you up are very, very, very tiny. It is a trick of how many particles are in you that you look solid. It is a trick of electrochemical repulsion that you feel solid. The fact of the matter is you are overwhelmingly empty. I know you've thought that about me before. The truth is, it's also true about you.
Oh.
Right? And so there we are. Now, the atom is the basic building block of matter. At least most of the matter that we interact with, the things we think of as being matter, this desk, you, the air, water, whatever it may be, it's all made up of atoms. What can you tell me about the atom? Yeah. Yeah, so atoms are the building blocks of matter. It's true. Chemistry is just Lego. It's just Lego that can explode, which I think we can all agree are better Lego. So atoms are the building blocks of matter. They can be put together. Does anyone remember this word? Compounds. Yeah, we can put atoms together and we make something called a compound. Who can give me an example of a compound? One that you know what atoms it's made out of. It's always the common example that people go to.
Dihydrogen monoxide.
H2O, dihydrogen monoxide, which of course is more commonly known as, yeah, for example, exempla gratia, H2O is water. And what that really means is that if you take one hydrogen and stick it to, if you take one oxygen and stick it to two hydrogens, you have water. If you take grade 11 chemistry, you'll learn specifically about like the angles and the shape of this whole thing, but it looks like that. We'll talk about that. We'll talk about what all those different things mean, but that's water there. My beautiful artwork no doubt impresses you.
Bro, if atoms are the building blocks of the universe, I'm arguing that God was just reading the instructions.
There you go. And maybe he was free building. Who knows? All right. Okay. So there we go. Atoms are the building blocks of matter. They can be put together to make compounds, and they are made up of three smaller particles. What are the three particles they're made of? Protons? Yeah, I'm going to use a different color for this. Protons, neutrons, and electrons. Very good. Hey, remind me, what's the charge on a proton? Yeah, so it has a +1 charge. And how much does it weigh? Does anyone remember? 9. No, not 9. If we're speaking German to your answer of 9, I'd have to say 9. I'll be here all day. anyone know?
2.
It weighs 1 actually, but 1 what? What do we call this unit? Does anyone remember?
1 proton.
Atomic
Oh.
mass unit. What a creative name, eh? But it weighs 1 atomic mass unit. What about the neutron? What's its charge?
-1?
I don't know. It's right in the name. Neutra.
9.
Yeah, 9 is right. There's no charge.
Oh. Okay. I was right in German.
That's right. The Germans are always right, except when they're not. Moving on. What does it weigh? It doesn't weigh nothing. It's mass. It's matter, so it's got to weigh something. Yeah, it also weighs 1. It weighs the same as the proton, basically. It actually weighs a tiny bit more than the neutron, or than the proton, rather. But for all intents and purposes, it's 1. And that leaves our friend the electron. What's its charge? Very good. And what does it weigh?
-1.
Negative weight? Negative weight? I don't even know what that means.
It floats.
That would be negative buoyancy, but that would still be that'd be positive buoyancy. That'd be a negative density, but still, it weighs very little.
Very little ammunition.
Very low mass.
Oh.
It rounds to 0 atomic mass units, but it doesn't weigh nothing. Does that make sense? It's like if you put paper on your bathroom scale, a piece of paper, it's not going to show. It's going to show 0. Does that mean the paper weighs nothing?
Yes.
No, it just means the paper is really light and the scale isn't designed to detect something that light. Does that make sense? Rounded to the nearest atomic mass unit, it comes out at 0, but that doesn't mean that electrons don't weigh anything. It just means that they're very low mass. Does that make sense? Is that review for everyone? Everyone remembers talking about that stuff? You're like, yeah, I love this. I remember this.
Yeah, let's go. I remember in French.
Did you say this in French?
Well, yeah, I learned
Oh.
in grade 9. I was in French school.
I did not
And
realize.
so, especially in math, and we have a lot of my stuff is kind of wacky.
Alors, je parle un petit peu de français, mais je parle français comme un
Well, I
idiot.
don't speak French anymore.
Moi aussi.
Like, I-
Hi, how are you? How are you doing?
Teaching the class in French, are you?
We're mixing it up. We did some German answers earlier. They went very well. Mr. Asher back there was unintentionally correct if we just switched languages. So now we're mixing it up.
I mean, can you ever be wrong if you just switch language?
In a universe with an infinite number of languages, what you've said is always the right answer somewhere. All right. Yeah, of course. All right. And this is going to bring us to reminding ourselves of our friend, the periodic table. Because we're going to today remind ourselves what atoms look like, the different ways we can represent them. And one of the main places we go to learn about atoms is atom school, I suppose, the periodic table. Periodic table contains a lot of information. So here I have a periodic table entry for what element? Incorrect. You're wrong, ISP. All right. So obviously, we're talking about aluminum here. What do we call this 2-letter abbreviation? Well, that's an L, actually. So AL, this is the short form for aluminum. But what do we actually call it? We call this its chemical symbol. Good. Symbol. Who can tell me about the chemical symbol? What are some characteristics of it?
Looks like an A and an L.
This one does, but of course, hydrogens would look like an H, and heliums would look like HE. Okay, so what are some of the characteristics of it? Remind me.
The chemical symbol is usually made up of characters from the English alphabet.
Yeah, good. So they're from the Roman alphabet, the same alphabet we use. Good. What else is true about them? This one's nice and intuitive. The name of the element is aluminum, and the short form is Al. If you're really good at Latin, all of them become intuitive. We have to watch out for some of them, right? What's the short form for sodium? Na. Why Na? Does anyone know? Not North America.
Not available.
Not available. Yeah, you think it was just a coding error? When they printed the first periodic table, they're like, oh, we can't find this Na. And they're like, oh, gotta run with it now. No, it comes from the Latin natrium. The Latin word for salt is natrium. So there you go.
Well, that shield is a kicking around.
Yeah, it's in the top here.
Oh, over here. I knew I saw it somewhere. Oh, can you read it? Yeah, Titanic, sorry. I'm just showing the kids. I knew I saw it, I just couldn't remember where.
Oh, it's talking to these guys.
Yeah, it's like a bunch of yahoos.
Yeah, they're terrible. They're the worst. You don't have to write this, but a couple things to note. It's always one or two letters. What else is always true?
They always symbolize it.
Yeah, the first is uppercase. And the second is always lowercase. Good. Good. And usually they're intuitive. There's some that are not. Does anyone know what Fe is?
Iron.
Good. What's another one? Does anyone know what Hg is? No. Mercury is right. Good. What about Pb?
Peanut butter and jelly.
Not an element. Lead is good. Because, of course, the Latin word for lead is plumbus, which is where our word plumber comes from, because pipes used to be made out of lead. By the way, if your pipes are made out of lead, don't drink the water. This is not good. Okay, anyway, so the chemical symbol is there. Listen, I don't make you memorize the first 20 or 22 or any of that nonsense. You will eventually memorize the ones we use a lot, because we're going to use them a lot. But you'll always have a periodic table in my class. I don't see any virtue, any value in memorizing the periodic table. If you want to learn like the song, that'd be cool. That's fine. Oh, have you never heard the song? Oh, look it up. Well, I'll play it here at the end of class if we have time. Yeah, it's fun. It's fun. Yeah, it's yeah, it's good. Okay, nope. Okay, so with that in mind, this number up here, what is this? It is the atomic number. What does it tell us? Sure, what's that mean? You're right, but what's it mean? Yeah, very good. It is the number of protons, and it is also, because, of course, if I touch a normal atom, if I touch this desk, or if I touch my face, or if I touch the metal here, under normal circumstances, do I get an electric shock? Sometimes I do, because sometimes electrons have been moved around, but usually most atoms are neutral, which means they have as much positive as they do negative. So if aluminum, for example, has 13 protons, how many electrons must it have? 13. Good. So the atomic number doesn't just tell us the number of protons, it tells us the number of electrons. It doesn't. You're right. We have to look a little deeper for that, but we're good. I have faith in you. Because what is this number down here? Yeah, this is sometimes called the atomic weight. I think mass is a better term for it. So I will typically call it the mass number, but you may see atomic weight, and that's fine. Now, what are the two things that weigh appreciably a lot? What are the two heavy parts of an atom? Protons and neutrons. Good. Now, all together, what does this weigh? So this is the average mass of the atom. Take grade 11 chemistry, we'll talk about why it's an average and not the exact one for every single atom. But it's the average mass of an aluminum atom. And it also ends up being rounded. It is the number of protons plus the number of, well, what two things are heavy? The electrons aren't heavy, they're super light. Yeah. So for all intents and purposes, this is the number of protons plus the number of neutrons. Does that make sense? If you put the two together, you get the mass. So if we round this, roundedly, what does aluminum weigh? 27. Good. So this would round out to 27, which would mean, how could I then figure out how many neutrons this has? Yeah. Why would I take away 13? Because it's the number of protons. So I could say 27 minus 13 equals what? Yeah, which is 14. Well, no, round this. 27. Yeah, round it. Because again, this is very close to 27. We'll talk again in grade 11 chemistry, which I hope you all take. We'll talk about why this isn't exactly 27. It's quite interesting. But does that all ring a bell? Everyone should remember figuring out how many protons, how many neutrons, how many electrons in grade 9. You should have done a lot of that, yeah? If you didn't, and if you're a little uncomfortable, do you really want me to label name? Fine. Are we happy now? There we go. If you didn't do a lot of this and this feels stressful to you, or if you did a lot of it and you just forget and you're like, hey, you're going way too quick with that, come talk to me. I'll give you a bunch of examples, and I promise after 5-10 minutes practice, it'll be like riding a bicycle, which is to say you'll have fallen down and scraped your knees. That's right. Questions about that? All right. Why don't we quickly do an example? You can sketch this on the side. I want you to use your periodic table and tell me about, oh, I don't know, let's say cobalt. Ooh, that's a good question.
I don't have space. What's it in
Use the back of your periodic table. Yeah, find some space. Lots of space. Use the back of the page. Use a blank piece of paper. You're creative. Number of protons, number of neutrons, number of electrons. By the way, protons and neutrons, we usually use uppercase letters. Electrons, we use a lowercase e. Why? I don't know. I just don't know. Yeah, I don't know. I don't have a good reason. That's just how we do it.
What's an atom's favorite flower?
No. Get to work.
It's a pea.
Nope. Get to work. Obnoxious. You know what I'm trying to get? You know the whiteboard tables in the whiteboard room? I have a request in right now to buy them for this room as well. I'm hoping. I hate these desks.
Are they going to be braided on these desks?
Yes.
All right.
Those are adjustable height, which is nice because these are too short.
Yeah, with these chairs.
Too short. Working on it.
I lost feeling in my leg.
Well, there's a silver lining to every cloud. Good. Yeah, you're doing great.
You're the one who took one.
All right, so what do we got?
Oh, that's where it is. I was trying to look for it, and then I
That's
just
so
like,
funny.
gave up on it.
You got it. I have faith in you.
So we don't write the one for electrons.
I want all three. I want to know how many protons, how many neutrons, how many electrons. Ah.
Oh, so that's just the answer.
Yep. Yeah, in a neutral atom, they should always be the same, right? There should be as many protons as electrons because a normal atom shouldn't have a charge. It should be neutral. So if there's 97 positives, there should be 97 negatives. If there's 12 positives, there should be 12 negatives. Who can tell me the numbers that fit into the periodic table here? What's the number up here for cobalt? 27. What do we call that, by the way? That is its atomic number. Good. And what's its mass number?
58.85.
Very good. Okay, now, somebody's already said, for the purpose of what we are doing here, what should I do with this number? Yeah, I should think of that as being 59, right?
It's 58.93.
Ah, interesting.
Yeah.
Okay. All right, so what does this 27 tell us? Okay, so specifically then there are 27 protons and 27 electrons. Does that make sense? Again, in a neutral balanced atom, these are always going to be equal because a neutral balanced atom doesn't have a charge. So if it's got 27 positive charges, it must have 27 negative charges. That's how you balance, right? All right. What does this 59 tell me? Obviously, I'm going to use it to figure out how many neutrons we have. So how many? Great. How'd you do that? You took the number and minus the number? I got to be honest, that wasn't a very helpful explanation. Schaefer, you know I love you, and I know you did it right, but let's try this again. I took the...
Mass
Very good. So I took the mass number.
and the number.
Very good. We subtracted that. Now, keep in mind, this is the total mass, right? That's what that means. It's the mass number. And this is the mass of the protons, right? Because they weigh 1 each. Nice and easy. And what does that add up to? 59 minus 27 is 32. And that then will be the number of neutrons. Well, that's interesting. So the number of protons ended up being 27. The number of neutrons ended up being 27. No, that's not true. Number of electrons being 27. And the number of neutrons was 32. Good. Questions about that? Does that make sense? Don't be shy if it doesn't. Now's a good time to talk about it. Okay. Now remind me, what is an atom in the Bohr-Rutherford model? Yeah. Bohr-Rutherford diagram? Bohr-Rutherford diagram. Oh, I don't know. I have no idea. Was that culturally insensitive? If that was culturally insensitive, I apologize.
I think my teacher may have skipped over this and they said, hey, you'll learn this in grade 10.
I bet you've done the diagrams. You may just not have learned the name, and that's okay.
She was an odd character.
In our model of the atom, now listen, I want to explain something. The model of the atom that we show you here is a simplification. It doesn't mean it's wrong per se. It means it's an oversimplification. Does that make sense? No different than like a map of a city is accurate. It tells you where things are in the city, but it's also an oversimplification, right? It's done with simple colors and straight lines, and it's just made to show you where things are. Does that make sense? You can think of these models of the atom like a map of the atom. Is it exactly what these things look like? No. And in fact, as you move on to higher levels of chemistry, you'll see much more complicated versions of what the atom looks like. But at its most basic, the Bohr-Rutherford model of an atom tells us, for the most part, where things are. And in Bohr's model, where do we find these three particles? In an atom, for example, where are the protons? They're big and heavy. Where are they? Kind of, sort of. I mean, think like one of the analogies we often use for the Bohr-Rutherford diagram is it's like a solar system, right? It's got a center part and things that spin around it. So if we're thinking of it as a solar system, what's the big heavy part of our solar system? Yeah, the sun makes up 99.9% of all the mass in the solar system, right? So the heavy parts of the atom are in the middle, in the center. What are the heavy parts of the atom again? Yeah, the protons and the neutrons. So in the middle, we have this structure that contains the protons and the neutrons, and we call it what? And we call it the nucleus. All right, and they exist the way they do because I don't like that circle. And luckily, I don't have to be content anymore. I have options. Watch this. I didn't really do it, but there it is. So we have the protons and the neutrons, just like that. And then we also have, I want that to be a dashed line. I wonder if that's an option. Is that something I can do? I don't know. I don't think I have the power to do that. So I'm gonna. Well, that doesn't seem more efficient, now does it?
Well, you want your dots and...
I'm just going to have to be very careful. So we have the nucleus, and it lives in the middle like that. And then, actually, you know what I could do? Watch this. See? I could just use... Oh, come on. Oh, I have to turn it on. That's why. I'm not in love with that. Not going to lie. All right, I can do better. I could have drawn this 50 times by now, but now it's personal. Okay, there we go. That's going to do. I don't care. Okay. By the way, yours is stretched because I'm struggling with the projector resolution. On my screen, it's a very nice circle. Yeah, I'm fighting with the resolution of the projector right now. And if I have it in its proper resolution, then it looks really small. You can tell me what you prefer, but I'm kind of the opinion that the extra space is worthwhile, even if it makes it look screwball-y. That's pretty small.
Yeah, but then the light.
Could you zoom out the projector?
I'm working on it. I have been building a lens and 3D printing a holder to go on it, seriously, so that it will expand it. Anyway, I only have so much free time. So we find the protons in the nucleus, neutrons in the nucleus, and then the electrons we find orbiting. Now, the electrons orbit the nucleus, and they do so in specific orbitals called shells. Now, each shell holds a specific number of electrons. Specific number. And so I'm going to sketch this out over here. But if we have the nucleus here with the protons and the neutrons, Does anyone remember how many electrons will the first shell hold? 2. Very good. I'm impressed. Does anyone remember how many the second will hold? Not 4, though you're on the right track. 8, correct. And we usually show them in pairs like this. We'll talk about why that is later on. And the third shell, not yet. The third shell actually also holds 8. And then it gets complicated. Then it gets messy. But the usual rule of thumb is this. They hold 2, then 8, then 8, then 18, then tears. Student tears. The tears bit? I support that. If we look at the periodic table there, who can remind me, what do we call the columns of the periodic table? I mean, I guess there's one thing we call them, but we actually give them a specific name.
Column is one thing you can column.
Oh, no, none of that. Does anyone know? Like a caveman. Look at this. It's ridiculous. It's how the cavemen taught science. That's all right. We'll make it work. It's a joke. All right. So we call the columns the groups or the families. Does that ring a bell? Group 1, group 2. All right. So the group number or the family number tells us what? What do we know about this? Well, if you look, let's take a quick notice. If we count across this first row, how many columns are there in the first row? Just 2. Can everyone see that? We have this one here and that one there. By the way, this isn't labeled, but what are these? What is this? Hydrogen and helium. All right, now, remind me, how many electrons did the first shell hold? 2, which means that this guy here has 1 electron in that shell, and it's not full yet, right? And then this guy here, which is what again? Remind me? Helium, has how many electrons? 2, and that's that shell full. Does that make sense? So everything, this has 1 electron, 2 electrons. And this, if they are in this row, it means they have one shell. Does that make sense? If you're in the first row, the way the table is set up, it means that that element must have only one shell of electrons. Does that make sense? And either has one electron in it or two electrons. What about everything in this row? Well, they would all have a first shell full, right? Because the first shell holds how many electrons? 2. So by the time we get to this guy who has 3 electrons total, he has a full first shell. And then in the second shell, how many electrons? 1. This would have 4, 5, 6, 7. And when we get to the end, that's 8, which, by the way, is a full second shell. So if your atom appears in the second row, how many shells will it have? 2. Would anyone like to guess what being in the third row means?
3 shells.
Yes. And what about the fourth? Very good. And I haven't kept going here, but the periodic table that you've been given has how many rows? Yeah, now the weird bit at the bottom is actually part of what row? Yeah, that's actually part of row 6 and 7. They just throw it at the bottom because otherwise the table would have to be wider than a piece of paper fits. Does that make sense? So if they put it in by making a gap, like they made a gap here, all of a sudden the table gets really, really wide. Yeah, go nuts. Dig in. So the row, yeah.
And Connor Morden to the guidance office, please?
Absolutely. So the row number tells us how many orbitals, how many shells an atom has. That's nice because it means that you don't need to do any math, right? You don't have to do any counting. I could tell you zinc, and you can tell me how many orbitals it has. Go ahead and do that. Zinc, how many orbitals? Oh, you should find it. How many orbitals does zinc have? 4. Good. How do we know that? In the fourth row. And that means the first one would be full, the second one would be full, the third one would be full, and it's only that fourth shell that would be partial. Does that make sense? What about silicon? How many shells will it have? Silicon. Yeah, 3, because it's in the third row, right? In fact, it is what? It's right here? Yeah, of course. One more, just to make sure we're all paying attention. Let's see if I can, what about gold? 6, very good. What's the symbol for gold, by the way? AU, from Quora, Latin for gold.
Memorize gold.
Nice. So the row number tells you how many electron orbitals it has, and then we know that everything but the last orbital will always be full. Does that make sense? It's only the outermost one that will be partial. How do we figure out how many electrons are in that partial shell? Yeah, you just count over. You just count over. So, for example, if I was talking about this one here, how many orbitals would it have? 4 orbitals, right? It's in the fourth row. How many electrons would be in that fourth orbital? Yeah, you just count over. 1, 2, 3, 4, 5, 6, 7. Oh, 1, 2, 3, 4, 5, 6, 7, 8. Oh, pretty sure it's 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. Don't worry about that yet. We'll talk about that. To get the number of electrons, don't worry about the number up top. Just count over. Does that make sense? Count over from the left. How many electrons does helium have in its outer shell? No, again, what do? We just count. So it is 1, 2. Does that make sense? You just count over. 1, 2. So it would have, we could even fill this in. This would have 1 valence electron. This would have 2 valence electrons. Does everyone remember the word valence? I just threw that out there, but we talked about it a lot. It just means outer shell. How many electrons would this guy have in its outer shell? Is that lithium?
1.
Good. Lithium has 1. What about this? What about beryllium? What comes after beryllium? What is there? Boron. How many does it have?
Would that be 3 or?
3. Yeah, you just count the actual elements. So don't worry about the gap.
Why couldn't we put the big
1, 2, 3.
put these ones over here?
We could. There's a reason we don't, and we'll talk about that. That's the other part of the way the table's arranged, and that's like Tuesday's lesson. Because it's a good question. Why not just shove it all so that it counts nicely? The reason is, the nice thing about this is, all of these have in common that they all have full outer shells. Does that make sense? That means they all behave alike, and all of these gases do behave alike. All of these guys almost have full shells. They're just missing 1. They're always 1 away. So they behave alike. We'll talk more about that later on. So really quickly, let me ask for shells and number of electrons in the outer shell for phosphorus. How many shells? How many electrons in the outer shell for phosphorus? So this is phosphorus here. What 2 things can you tell me about it? Good. 3 shells. Now the first shell will be full. The second shell will be full. But the third shell has how many?
5.
Very good. I think 1, 2, 3, 4, 5. Does that make sense?
Is there like a maximum amount of shells?
Hypothetically, could we just add another?
I mean, yes. So the biggest element that we've ever created, I'm trying to remember if we've gone beyond Oganesson 118, but everything beyond, well, everything you see with round brackets down there, we're getting into pretty unstable stuff that doesn't hold together very well.
Stuff that we made.
So some of it occurs naturally, some of it we've made only in the lab, but these are things that don't hold together well because they have trouble staying stable for exactly that reason. So there's not like a hard and fast number of the maximum possible shells, but as you get bigger, you get less stable. Which is why eventually, higher up on the periodic table, everything is radioactive because everything falls apart because it's not stable. I do not like being stuck to this desk. I'm not a fan. Anyway, let's do one more. Why don't you tell me about iron? Iron. Tell me what you can about iron. Oh. What's the symbol for iron? Very good. Yeah, talk to me. What do we know about iron? Yeah, this be.
It's got 4 shells, and the last one has 8.
I once cracked an egg with 2 shells.
Very good. How did ISP get that?
From the Latin word.
Yeah, we figure out what row it's in. That tells me how many shells it has. And then how did you figure out that there's 8 electrons in its outer shell? Sorry? Yes. How? Yeah, it just counts over from the left, right? Does that make sense? Does everyone remember doing that? Did you do that in grade 9? No, this is new? All right. So this takes a bit of practice. That's okay. We'll get some practice. But this is why the periodic table is shaped and set up the way it is. It's not just randomly designed to be confusing. In fact, it's designed to be helpful so that you can quickly look at it and get information that's useful to you. Yeah, yeah, of course. Okay, so with that in mind, let's remind ourselves how we draw a Bohr-Rutherford diagram, and let's start with aluminum. So first of all, on the periodic table, where do we find aluminum? Yeah, it should be right. It should be right here, right? Okay, what does that tell me then? What do I know about aluminum? Very good. So, see how we did that just by looking at the periodic table? Didn't have to do any math, didn't have to do any crazy work. The table's set up to tell me that. Is there anyone not clear on where we got those numbers? Be honest. Trust me, you're not going to hurt my feelings. We're not going to point and laugh at you. All the pointing and laughing will be aimed in this direction this semester, I promise. And I can take it sometimes. One of the first things people notice about me. So, we know about aluminum then, that it's what number? And what's its mass? Okay, let's just round it to, okay, 27. So the first thing we already know from up here that it's got 3 shells. We know it's got 3 electrons in its outer shell. What does this 13 tell me?
That's the mass of its protons and electrons.
Very good. So it's got 13 protons and it's got 13 electrons total. And we already know where they go, right? Because how many fit in the first shell?
2.
And that's full. How many fit in the second shell?
8.
And that's full. And how many are in the outer shell?
3.
Right, we already knew that. The only thing I didn't already know is what's this 27 going to tell me?
Well, it won't tell you anything until you subtract the 13 from it.
Very good. So what is 27 minus 13?
That's 14.
Great. And what is that number? That is?
Croutons.
It's the croutons. Very good. All right. So now, to draw a Bohr-Rutherford diagram, we want to do this nice and neatly. All right? Nice and neatly. Nice. Richard, how do we want to do it? Neatly. Do we want it to be really messy?
Yes.
No, Richard, we don't.
We can't all do the perfect magic circle.
I had a high school teacher who made us use a compass to do these. Yeah, like, you know, the old, like, with the pokey stick and the pencil goes on, he insisted. And if you didn't, he would give you 0. Yeah. I'm not quite that intense, but honestly, if I can't read it, I'm not marking it. Only a big old 0. Be neat. All right? Okay. Now, what goes in the nucleus again? Remind me.
The neutrons.
Great. And how many do we have? How many neutrons?
Oh, neutrons. That's right.
How many? 14. So we're going to say 14 neutrons. What else goes in the nucleus? That's a terrible N. 13 protons. Stop. Okay, so there you go. Now, how many shells does this have? What did the periodic table tell me? 3. My advice, don't worry about anything else. Just draw the shells first. Make sure they fit nicely. It's nice to use kind of dashed lines like this. You could use a different lighter color. We're creative here. We're just making happy little electron shells.
Was he? Wasn't one of those guys?
Okay, I don't want to say that's really good, but it's not bad, that's for sure. Okay. And then, how many electrons fit in the first shell? Great, and we always know the first shell is going to be full if it's got 3, so we can just draw them in. How many fit in the second shell?
8.
And we don't have to think, if it's got 3 shells, the second one's also full. So we can just go ahead and do that.
I'm imagining an aluminum egg, and then you crack it open and there's another shell.
No, don't judge me. I'm doing my best. And how many now? This is the first thinking we've really had to do. How many fit in the outer shell?
3.
3. And we got that information from the periodic table, right? It told
Where
us.
was that 3 go? That's what-
Wherever you want.
Now, a neat rule of thumb, like as in not like this is neat, but rather a good way to be neat and organized, is always put them kind of north, south, east, and west. Don't just randomly scatter them around.
But aren't they supposed to be paired? Have a little buddy.
Everyone gets one first, then they pair up. So like if you're drawing 5, all 4 corners would get one, then you'd start doubling. Good question. Yeah.
So it's like hanging out cards.
Yeah, that's right. The dealing cards. Very good.
Except you're dealing.
I never thought of that as an analogy. That's a very good one. I always use the analogy it's like having children, which is give all the electrons to your favorite child first, and then the rest can figure it out.
God's favorite.
Is that bad to admit? Whatever, it's the truth. All right. So there we go. That is a Bohr-Rutherford diagram. I'm kidding. I don't like any of my children. That's a Bohr-Rutherford diagram of aluminum right there. The baby's all right. He's pretty cute.
Yeah, but they get stinky.
Oh no! Oh, how sad.
Oh, no.
Oh, I thought he was
It
bleeding.
might be the blood of my enemies. We're not sure.
Oh, you just
All I'm saying
stabbed
is-
him with it?
Somebody put the electrons around randomly, and this is what it looks like.
Thanks for sharing.
That could be you. All you have to do is be messy. I'm so glad I record these lessons. I miss gelling. What was I going to accomplish at this point?
What, so now he can stain his
You know, oddly, it doesn't appear to be anything. I think it might be the blood of my enemies. All right. Have I injured myself in the line of duty? All right. That's a Bohr-Rutherford diagram. I'm going to have you do a few, but time is short, so I'm going to have you do those few for homework.
Oh, fine.
Yeah, you're welcome. Okay. Now, the last thing is this. Yes, I am. We have a simpler diagram that we use because drawing Bohr-Rutherford diagram sucks, and we never actually do it in chemistry because it's a big waste of time.
Why did you put this?
Amen, brother.
Because you gotta understand it.
Right?
You gotta understand it. It's like math. I want you to know your times tables intuitively because that will be helpful sometimes. Then when we actually get going, I want you to use a calculator because I don't have all day, right? I want you to be able to graph by hand because it's important to understand how graphing works. Then I never want you to do it again in the real world because computers do a much better job.
Right? Do you do the thing where you have to write what the little cell looks like? And you have to do the circle and everything? And you have to label it?
Like for microscope diagram? No, we're gonna take pictures. We'll talk about it. Okay, so a Lewis diagram is a simplified diagram showing only the outer shell of electrons. No, it just shows only the outermost shell.
How do you know how many cells there are?
Well, just by looking at the periodic table. That's the nice thing, is the periodic table tells us that. Now, who remembers what do we call that outside shell? We call it the valence shell. Now, here's the interesting thing. Chemistry, 99% of the time, is just about that valence shell. That's where chemistry happens. The outermost shell of electrons on an atom is unstable. It is looking to either gain or lose electrons or share electrons. And those electrons are really what makes chemistry happen. So when it comes to studying chemistry, 99% of the time, discussing this valence shell gives us all the information we need to do chemistry. So why would I draw the protons and the neutrons and the innermost shells if the only thing that's really going to make a difference is the valence shell of electrons? The answer is we don't. Does that make sense? So the valence shell is the bit of an atom that does the chemistry. It's the reactive part. So that's the part we want to be able to draw. You're never going to do another Bohr-Rutherford diagram beyond the one I put on this unit test because it's part of the curriculum, so I gotta cover it. But in this course, that's it. That's the last 4 Rutherford diagram we'll draw. But Lewis diagrams, what we're showing here, the simplified one, you're gonna draw lots of them. It's actually really useful because they include the part that's helpful. So here's how it goes. We wanna draw, what did we do as our last example, aluminum?
Yeah.
Let's do it again. In the Lewis shell, I don't care about protons and neutrons. So I'm not going to write how many protons and neutrons. I'm just going to put, yep, but I've got to show that there's a nucleus there. I got to show that it's an atom. So what am I going to put to show that it's aluminum? I'm not going to say 13 protons, 14 neutrons. I'm just going to put the symbol. I'm just going to put Al. So we start with the chemical symbol. And now, the only thing I care about is the outermost shell of electrons, right? How many valence electrons does aluminum have? 3. And does everyone remember how we find that on the periodic table? I just count over, right? So to get to aluminum, we have to go 1, 2, 3. So it has 3 electrons. Now, how do I arrange them? That's right. And you can, it doesn't matter where you start. In this case, I'm going to go like that. And for each electron, we show a dot. So all we need is the chemical symbol. And each dot represents a valence electron. Yeah.
Okay, so we're not doing any of the Bohr, Ruther, or whatever ones because the periodic table already tells us the answer, right?
Great, we have all that information.
So why are we doing this one if the periodic table also tells us?
Because you're going to find that drawing this is really helpful when we go to actually do stuff.
Really?
Oh, yeah, absolutely. Yeah, listen, some people may be able to do it all in their head, and that's great. But for most of us, being able to draw it out and actually show what happens with the electrons is super helpful. But showing the neutrons and showing the inner electrons would just make it confusing. So let's do a second one together. Magnesium. First of all, what's the symbol for magnesium? Be careful. You're hearing Mn and Mg. So the question is, who am I failing?
MG.
I was right, never mind. MG.
What's manganese?
Manganese is just a different atom. So magnesium is Mg. Now, here's the nice thing. On the periodic table, where do we find magnesium? Should be right. Right here. There it is. I want my really big one back. I'm going to buy another really big one. I might paint it on the wall myself. Anyway, there's magnesium. Yeah? So here's magnesium right here. How many over is it? 2. How many electrons does it have in its outer shell? 2. That's it. If I wanted to know how many shells it has, how many shells does it have? 3. There we go.
We're experts already.
Yeah, that's it. And how should I draw these on? Should I draw them like this? No, I'm not Swedish and I'm not making an umlaut. I'm going to do this, though if you did east and west, that'd be fine.
It has to be even on either side.
Whoa, whoa. Either would be fine. All right, there we go. And what about chlorine?
Yeah.
Yes, what's chlorine symbol? Cl. And how many valence electrons does chlorine have?
2. Wait, no, it has a lot. It has 7 2.
Well, let's take a look. Chlorine is over here, right? So we would have 1, 2, 3, 4, 5, 6, 7. That's almost a full shell. How many would have been a full shell? 8. And it has 7.
Or number 7's all wrong.
So let's draw them on.
Wait, so argon is just chlorine with an extra buddy?
That's right.
That's messed up.
No, yeah, that is messed up.
So if you drink argon, is that equivalent to bleach? A little extra?
That was interesting.
What did it do?